this operator in a usual like 2-particle state, which is what we had for the scattering event. We had 2 incoming particles. We know that kind of the expectation value of this operator classically just goes to this action, this on-shell action that we discussed at length, right? And the other thing that we need to do to take a classical limit is to kind of unquantize these commutators, right? So typically when we do canonical quantization, we have a theory with some phase space, with Poisson brackets, and then we replace the Poisson bracket with IH bar times a commutator. Here we're gonna undo this. So the statement is that whenever I have minus I over H bar times a commutator, this will just give me a Poisson bracket. Okay. And that will give me that formula that I wrote in the first class, which is that this out operator in the classical theory, so now this is a classical observable, so actually not an operator, it's just some function in the phase space. This will be given by the original one plus the Poisson bracket with this classical action in other words, it will be this kind of the classical S matrix will be this adjoint action with Poisson brackets on the initial operator. Okay, so this is this S classical that will map kind of, depending if you take kind of the Schrodinger or Heisenberg-like picture, even though we're talking about classical mechanics, it will map either the in-phase space to the out-phase space as some canonical transformation, or in operators to out operators, or in functions of phase space to out functions of phase space. Okay, is this clear? All right, so let's compute an example to see that this really works. Okay. Oh, so first of all, let me comment. So in order to do computation, we need to remind ourselves what these Poisson brackets are, right? So, and we just have like a pair of particles, right? So the phase space, so this is just the set of like kind of xi and pi for each particle. And they have the usual canonical commutation relations. So we have that kind of pi, pj is 0, xi, xj is 0, and xi, pj is delta ij. Okay. Okay, so these depend on time, but this is that I'm using the Heisenberg-like picture, so these are all at fixed time. But actually, we wrote our amplitude as a function of the impact parameter, so we need to be a bit careful. So what is the impact parameter in this language? So just so the impact parameter was a function that was orthogonal to the initial momenta or velocities, right? So actually, we need to write the impact parameter because to understand how it's made out of these variables, and it's something pretty simple. So let me just project onto the orthogonal directions. So this will be eta mu nu minus, so let me define this object in a second. So this thing here, this is simply a projector onto the perpendicular direction, and these W's are the duals to the velocities, right? So this W, you have Wi Vj equals delta Ij, and kind of Vi is just pi over mi. Okay, so if we have this formula, we know how everything depends on momenta and on the coordinates, and then we can go ahead and try to compute these Poisson brackets. So let's do it. Let's compute the simplest observable, which is just a change in the momentum of one of the particles. Okay, so I want to ask the following question. So I have this pair of particles that were coming in, so they're going to interact gravitationally. They're going to deflect, right, because they're exchanging gravitons. And then this one had like P1 initial momentum, P1 in, and then at the end, it will have P1 out. So the quantity I want to compute is delta P1 mu, which is P1 out mu minus P1 in mu. Okay. And using that formula here, at leading order, the difference will just be the Poisson bracket with the action integral. Okay. So this will be given at leading order as simply the following quantity. Okay, so let me remind you what the action integral was. So the formula that we wrote for the action integral a couple lectures ago was the following: G m1 m2 squared. There was like sigma squared minus 1 over d minus 2. So remember, this sigma was just p1 dot p2 over m1 m2. So it's just the product of the velocities, p1 dot p2. And then it was the transverse Fourier transform in of the exchange momentum. So then I had like a d dq e to the I q dot b delta 2p1 dot q delta 2p2 dot q, and then 1 over q squared, which was just the graviton exchange pole. So now we can just apply the Poisson bracket to this expression. Right? So in general, what is the formula for this kind of Poisson bracket? There's a shortcut, right? We know that when you take the Poisson bracket with one of the canonical variables, it's simply the derivative with respect to the other variable, right? Because remember, the Poisson bracket is ddx ddp minus ddp ddx, and this one is just one of them, so this will be simply the derivative of this action integral with respect to x1 mu. So that's easy to compute, because where is the only place where we have dependence on x1 here? Sorry? B. Yeah. Right? Like everywhere here, right, we are taking the commutator with p, so p commutes with p, but it doesn't commute with x, right? So which means that this derivative, the only thing that it sees is the exponent here. So let me write a formula over there, because then we'll compare with slightly different calculation. The zero component, it depends on which frame. But for instance, if you go to the rest frame of any of the two particles, right, then this is orthogonal to the velocities of both particles. This is what this projector means. It's projecting onto the orthogonal subspace, right? So this p mu, if it acts on like v1 nu, it's 0, or if it acts on v2 nu, it also gives 0. So it just kills the the component along these velocities, right? So in that frame, the 0th component is just 0. So this is purely space-like. Yes, but I do. Like, I just need to solve this relation. I could write an explicit formula if you wish. It's not very illuminating. Yeah. I mean, let me do it. Yeah, okay. Okay, so let me write the result here, because we'll compare in a bit with a slightly different calculation. So what is the result? The result is that delta P1 at leading order, just G M1 M2 squared, and then the Fourier transform. So this sigma squared minus 1 over d minus 2. Actually, there was an 8 pi, sorry, which I forgot, because this was this kappa squared. So this is important if you actually want to get the right answer. And then the commutator just acts on the exponent, so it takes a derivative of the exponent. So we just have the following. We just have ddq delta 2p1 dot q delta 2p2 dot q, then iq mu over q squared, right? Because it just takes a derivative with respect to x1, which appears in the exponent, right? And then any other component would be killed by this. So I just get like 1 power of q down from the exponent. Okay, so let's just leave this here for later. And this Fourier transform is very easy to compute. And so as an exercise, you can just finish the computation and get the actual answer in terms of just the velocities and the impact parameter. So you just need to understand how to compute this Fourier transform, which was actually very close to one of the exercises. So one of the exercises in the problem set was to do this by first doing the Fourier transform and then computing these commutators. Okay. But now there's an issue here, because we've been considering only kind of these 4-point processes. So what about radiation? Ultimately, we want to talk, the title of these lectures is Scattering Amplitudes and Gravitational Waves, and so far there haven't been many gravitational waves, right? So what about radiation? Okay, so there's two options. The first one is we can play exactly this game, but extending the phase space, right? So if we actually want to have gravitational radiation, here we're only discussing the phase space of the pair of particles which are interacting gravitationally. But if you want to understand the radiation, you would have to extend the classical phase space to include the gravitational field, right? So option 1 is extend this phase space to include the gravitational field. But this is famously subtle. Why? Because gravity is a gauge theory, right? So we have the principle of general covariance. So there's a bunch of gauge degrees of freedom. So if you want to actually compute things using Poisson brackets, you need to do it very carefully. In a gauge theory, you have to use Dirac brackets, impose the constraints on the phase space. Okay, it's a whole endeavor. You were playing this kind of game also, in a sense, during Alejandra's lectures. Okay, so this can be done, but it's subtle and it's not particularly nice. There's also something like this secretly in this word line calculation, because if you write a theory for a relativistic word line, that is also a gauge theory because you have time reparameterization invariance along the word line, which is basically a dynamical gravitational field on the word line, which is pure gauge. And for instance, that tells you that you can write a reduced phase space that instead of having P's and X's, just has P and B. But then, because of this funny definition of B, it turns out that B doesn't anti-commute with B in the sense of Dirac brackets. Okay, so I didn't write this relation, but you would write some complicated commutation relation, which would be B mu, B nu. So this is a Dirac bracket. This would be something like 1 over M1 B mu W1 antisymmetrize plus the same thing with 1 exchange with 2. Okay, and this will be only up to constraints. Okay, so even in the word line, if you want to do this just not from the final answer, but from some action principle, it's slightly subtle because the word line, relativistic word line, actually it's a gauge theory. Just like in string theory, we have also like worldsheet reparameterization. We have to fix conformal gauge or whatever. The same is true for word line. And it's even worse in actual gravity. Okay, so we don't want to do this. So we are just going to now take the quantum back to the quantum root, and we'll see that it's very easy to understand radiation directly using the quantum perspective. Okay, so option 2 is to go back to the quantum way of writing things. So this proved useful because we understood a lot of things about this classical object, this classical action by thinking about this relationship with the scattering amplitude. So let's do the same now for these other observables. So option 2 is the quantum way. So the quantum way, remember, is that if I want to look at this, where this is just the usual S matrix. Okay. So now I'm going to massage this formula to give something that is more directly related to the scattering amplitude, and we'll see precisely where radiation can come in. Okay. So first of all, I'm going to do, as we usually do in the quantum theory, and just write S as 1 plus IT. Okay. And also, I'm going to use unitarity of the S matrix. So unitarity of the S matrix tells me that S dagger S equals 1. Right? I can also write this as 1 minus I T dagger. It's 1 plus I T dagger, sorry, T equals 1. So this gives me the following relationship. This tells me that minus I T dagger, which is this term here, plus IT, which I can move to the other side, and then I have some cross term here. Okay, this is just from solving this relationship. I can find a formula for T dagger in terms of T and the square. Okay. If I move this to the left-hand side, this would be the usual optical theorem that tells me that the imaginary part of the amplitude is related to the cross-section. But here, I will use it in this form. Okay, so now let's use this expansion here. S dagger OS minus O will be 1 minus I T dagger O, 1 plus I T minus O. Okay, so let's look at various terms. So 1 times O times 1 cancels precisely with this term so that we can throw away. Then we have minus I T dagger O times 1. Then I have 1 times O times IT plus I O T. And then I have this times this times this, which just gives me T dagger O T. Okay, but I still don't like this formula, so I want to get rid of this T dagger over here. So let me use that relationship with derive over there, where I can replace minus IT dagger with minus IT as long as I correct by this term over here. Okay. So this thing will be minus ITO. I need to correct, so I need to add minus T dagger TO. And then I will have this term here. So this is this term. Okay, but this is very nice because it has you arranged in a particular way. So this, yes. Sorry, say it again. Did I? I think there's a missing minus sign. Yes, this is minus. You're right. Thank you. Okay, so these two terms, they just combine into a commutator, right? Because I have OT minus TO, right? So this will be I OT. And then this term and this term, they also combine into a commutator of T with O, right? So this is going to be plus T dagger, and the commutator of O with T. Okay, and this kind of makes sense, right? So this was this delta O when evaluated in some state. So this is telling me that if I want to understand the change, I will have to commute with the T matrix, which measures the difference of this observable between the in and the out state. But there's this extra term here. So let's see that this term is what will give rise to kind of additional things like radiation and stuff like that. So let's plug this back into our original formula. Where we had our state, and now we'll have an I OT plus but here I can massage it even more because I can insert a complete set of states. Okay, so let me insert here just the relationship 1 equals sum over all the states of the theory, just a resolution of the identity. So this will give me the same term I have here. And then the next term will just give me sum over all intermediate states. And you see that this has a very nice interpretation. This is just measuring the change of the observable in whatever state I had originally. This is saying that there's another option. My original state can evolve into some other state and make this observable change, right? But then there's some probability for that to happen, so I need to kind of square with T dagger. So we'll see that this will look something like a cross-section because it's quadratic in T, whereas this is simpler. Okay. So let's keep going, and eventually we'll reach the same formula that we wrote before. So to finish the calculation, I need to actually tell you what this initial state was. By the way, this formula has a name. This is called the KMOC formula after Kossauer, maybe, and O'Connell, which were the first to think about these observables in this informalism, but in this language of scattering amplitudes. Okay, so what's my initial state? So this is a state in a quantum theory, so I want it to be just a pair of particles which are going to scatter. Okay? So I'm going to have an integral over the on-shell phase space of two particles. I have P1, P2. I'll have some wave function for P1, which you should think of as a wave packet, which is peaked around some like classical momentum. Its form won't matter too much. These have to be on shell, right? So I have to have theta P1 0, delta P1 squared minus M1 squared, delta P2 squared minus M2 squared, like theta P2. And from now on, I will save energy by writing these as kind of delta plus of something, where the plus just means I need to pick up the positive energy part. And I want these two particles to be separated by this impact parameter. Remember, we wanted to scatter these two particles, but we wanted them to be separated by some distance b. Right? So these I just need to add a phase, say that P1 is translated by an amount b compared to P2. And then here I just have a P1, P2, usual two-particle state in the theory. So these, let's just take them to be scalars. Okay, so we're going to plug this in here. But notice that we will have two copies. So we need to have two such states. And of course, I should choose two different labels for the states. So this delta O will be something like this. So it will be some integral where I have P1, P2, P3, P4, where P3 and P4. So I'm going to label the ones here as P1, P2, the ones here as P3, P4, because I have two copies of the states, right? But this one will be complex conjugate. So the wave function needs to be complex conjugate. So here I'll have P1, P2, P3 star, P4 star. Then I will have all the on-shell delta functions. So let me just write them as pi squared minus mi squared. I will have the exponent, which will be P1, and then the other particle that is P1 here, I will call P4, right? So the picture that we always have in mind is the following. We have this scattering of P1 that has M1, P4 that still has the same mass, and then P2 that has M2, and then P3 that still has M2, right? And usually we write P3. So now let's go back to incoming and outgoing notation, which will be a bit more familiar. This will just be P1, P2 minus Q, and P4 will be P1 plus Q. So this is just the momentum transfer. Okay, so here, because P1 and P4 were the ones that were translated by this phase, I'm going to have P1 minus P4 dot B. And then just matrix elements. So then I will have the same thing that I had here. I'll have P3, P4, and then OT, P1, P2, sum over X, P3, P4, P dagger, X. Okay, we're almost there. these are wave functions. So just wave packets. Imagine that I want this to actually be two particles that are scattering, and I'm setting up some quantum state, and I want them to be localized around some classical trajectory that has a fixed forward velocity, et cetera, et cetera. So it won't matter in the end what they are. It won't matter, yeah, because we're just interested in the classical limit. If you were computing this observable in the quantum theory, then you would need to tell me this. But here, it just matters that as I take h bar to 0, this peaks around some classical position of the particle. Okay, and we just need one more step to massage this formula, which is that I'm going to change variables, because notice that, okay, so if I choose an operator, like the momentum or the energy, these things are eigenstates, okay? Which means that I will just have the S matrix, and this object will conserve momentum. So this will be proportional to momentum conserving delta function. We'll do that in a second, where we'll choose a specific operator. But let's just assume that there's a momentum conserving delta function in this matrix element, right? Then I should be able to change variables to these things here. Okay, so let's actually do it. Let's choose O to be now the momentum of particle 1. Okay, so let me choose O to be this operator. So what is this operator? Okay, this is going to be dd p prime delta plus p prime squared minus m1 squared, and then just a dagger p prime a p prime with p prime mu as a quantum operator. So something very simple. So what's going to happen here? So if I have p in the commutator, one of them will act on this side. It will act on p4. It will just give me an eigenvalue, right? So let me just do it step by step. So if I have p3, p4, and then I have the commutator of O, which is p1 mu t minus t p1 mu, and p1, p2. Then when it acts on this, because p4 is the momentum of particle 1 in the final state, this will just give me p4, right? So this will give me p4 mu minus p1, which is what you get when it acts on this one, and then just the matrix element, which is the scattering amplitude. And this is just the amplitude times the momentum conserving delta function, of course. So I have p1 plus p2 minus p3 minus p4. Okay, and this term here, there will be a similar manipulation. But notice that this is quadratic in t. So this will start at order g squared. So let me ignore for a second this term, because we just want to match this formula here, the leading order impulse. And then I'll comment on what's the contribution from this. Okay. Yeah. Because of this picture here. So here I have like two distinct particles. So let me draw the lines slightly different, right? So I have particle type 1, particle type 2. Its momentum changes in the scattering process, but I'm trying to measure the impulse of particle 1, so the change in the momentum of particle 1 in the scattering process. So this only acts on P1 and P4. Yeah. But this is just Q, right? This is just the momentum transfer. So the formula that we get is very simple. So let me plug this back into that whole mess, but changing variables, so that P3 and P4. So I can change both of these to be just P1 minus Q, P2 minus Q, because I have momentum conservation, as long as I get rid of that momentum conserving delta function. Okay? So I will have 3 integrals over momenta left over. Let me choose them to be P1, P2, and Q. Okay, so the change in momenta of particle 1 then will be something simple. So I will have ddp1, ddp2, actually maybe I can make it even more clear by choosing the wave functions here to have labels for the 2 species of particles. Sorry? Sorry, yes, thank you. Okay, so I have this whole thing, and then I have ddq e to the I q dot b. I have, here I had 4 momentum conserving delta functions, but now I change P3 and P4 to be P1 and P2 minus Q. So this is going to give me delta 2P1 dot Q plus Q squared, delta minus 2 P2 dot Q plus Q squared, right? And then from this term here, and I will remember that I will have an I here, which I forgot. I will just have IQ times the amplitude. Okay. So what is the role of all of this? So as usual, we are in the small q squared limit compared to p, right? So in the small, when I take q to be much smaller than p, then these transverse delta functions, they just precisely correspond to the ones here. And actually, this combination, because the radial action was just the Fourier transform of the amplitude, I can recognize as precisely ddq to p1 dot q iq mu times the amplitude, right? So you see that this whole object over here precisely matches the calculation that we did just using classical mechanics with the radial action. And what's the role of this thing? This is just there to make sure that we are around some classical trajectory. So if I expand this also for q small, right, so I will have the whole thing in the brackets with P1, P2, and just the absolute value of the wave functions of particle 1 and particle 2 in the small q limit, which is the probability of having this particle, right? So this is just telling me that if I do the calculation in the quantum theory, I will get the classical expectation weighted. So here I will have the kind of P1 mu classical, which was the thing within the parenthesis, weighted by the probability of having this particle in the initial state. So it makes sense. So this precisely corresponds to the calculation that we did in the classical theory at leading order. But we drop another term. Remember, there was this term with the intermediate state. So let me pictorially tell you what this corresponds to. Right, so pictorially, this delta P we said that it's given by this thing. So let me write this as some double bracket of P1 classical, where by the double bracket I just mean the expectation value of having this particle in the initial state, right? So this will be simply this double bracket of kind of the Fourier transform of Q times the amplitude with a factor of I. So that was the first term. And then I had the other term. So this one, as a picture, is just Q mu times just the amplitude. And the other term that had the S matrix squared, so what is this? So the other term that schematically took the form kind of P, well, actually, that within the brackets we had P3, P4, P dagger, X, and then so pictorially, this will be as follows. So this will be just the impulse in some process. So the same thing as before. So I will have kind of my two particles in the initial and the final state, but I can have some additional states X. Okay, so I'll have P1, P2, and then maybe here I have like P2 minus some L, P1 minus plus some L, which is not the total transfer, right? Because this is some intermediate process, right? And then on the other side, I will just have the amplitude for that process, and here I will measure this quantity, right? So this will be multiplied by the momentum transfer, which will be this L mu with an I. Sorry, without the I. And here I'll just have the complex conjugate of this. So here I have P4, P3, and then P1 plus L, P2 minus L, and this is on shell. Okay, so this looks like a cut of the 4-point amplitude weighted by something, or alternatively by the cross-section of producing additional states, and then just weighted by the momentum that is measuring the impulse of the particle in that intermediate state. Okay, so there's two contributions. One, if you wish, that doesn't see the radiation explicitly, which is just what is the impulse in the 4-point process. But then the second contribution to the formula knows that there can be additional radiation in the final state, right? So it's computing kind of the impulse coming from whenever I have radiation in the final state, which will be added to that one. Okay, and because this is a 5-point amplitude, this contribution actually is of order G cubed. So we won't compute this because this is really like a two-loop calculation. Okay. Okay, any questions about this? Yes.
The first one, shouldn't we have some H-bar factors on this?
Yeah, here I'm setting H-bar to 1 again.
Okay.
But because delta P1 is a classical observable, actually what happens here, remember we had all these like 1/h bars that when we computed the classical phase, we had to exponentiate to get rid of. In these formulas, actually what happens is that there is a cancellation between these two terms. This one will have 1/h bars if you go to high orders, right? And this one won't. So for instance, at one loop, which is where we had this issue that there was a box diagram inside of the 4-point amplitude, right? Here, there will be a contribution where the final state is just the two particles. I don't have anything else, which is something I can have at one loop, right? That won't be a contribution from radiation. That literally will just subtract the imaginary part of the amplitude weighted by L, which will precisely cancel this 1/h bar piece that canceled also when we exponentiated. Okay, so this, the quantum calculation, if this is a classical observable that has a well-defined h bar going to 0 limit, it works out at the end of the day but thanks to cancellations between these different terms of the formula. And as you go to high and high orders, you need to kind of expand this to sub and sub leading order to extract the classical piece, just like we had to do when we computed the amplitude.
Okay. And the other question would be in remarks to the weight on that cut. Like, it's kind of weird to see a weight in this type of cut. Like, what would be
so I will give you another example now that maybe will make it less weird. Okay? Which is just the radiated energy. So let's compute an observable which is purely relative. This one, the leading contribution, which is this one that we computed at tree level, this was a purely elastic contribution. But now we'll compute the energy radiated and see that it's really inelastic, and we see that it's very natural to measure something.
So just a naive question. So there, X carries no momentum. Is that obvious? Why that's
no, X carries, sorry. Yes, you're right. This, I need to add Kx. Yes, sorry, you're right.
Okay. And then it's not L mu, it's L mu plus Kx, right?
Yeah.
Multiplying the...
well, it depends which particle we are measuring. So the way I labeled, but it depends on how you label the amplitude. Yeah.
So the bottom leg is particle 1, the top leg is particle 2.
Yes. Yeah. Actually, that will be important now, because now I'm going to compute, instead of this impulse that has these contributions, let's do another example. So we'll do two more examples. One will be the radiated momentum in the scattering process, and the other one will be the actual waveform for the gravitational radiation. Okay, so example 1 will be the radiated momentum. So what is the operator here? Let me call it K mu to distinguish it from the one from the particles. This K mu will just be the momentum carried by the gravitons. Okay? So what is the formula for this? It's very similar to the one for the momentum, right? So this will be like sum over helicities of, and then some on-shell phase space for some graviton momenta. So this will be delta plus now just K squared, because they're massless, and then A dagger K with some given helicity, and AK with the same helicity. Okay? And now the formula will be much easier, right? Because if we want to compute this delta K, well, actually, there is no delta K. Delta K is just K out, because there is no radiation in the initial state. Okay? And that means that we can ignore the first term, because the first term, right, if we just do the usual KMOC calculation, or the usual calculation that we did, there will be a term that just looks like this, K mu T. But K mu acting on the initial state is 0, because I didn't have radiation originally. So this is simply 0. So we just have the other term. And also, because there's no radiation in the initial state, I can write it in a simplified way, just as T dagger OT, so KT. Again, because K acting on the either side is just 0. Okay, so it has to be sandwiched. But then see that it's only the second type of contribution that appears here. And this measurement operator, right, will just be the momentum carried by X. Okay, so this will give a very natural formula for the radiation, which will be the following. So once again, we'll have, now it's kind of this K mu radiated. So we'll have the usual story with this wave function. Actually, let me write it over there, since I already expanded. So I will still have this classical expectation value. And then I'll have, again, the Fourier transform. And then I'll have sum over intermediate states of P3, P4, T dagger, X. I realized that here I was being a bit sloppy because in principle the intermediate state includes also the two particles. So what I mean by X here is slightly different than here, but I hope it's clear. And then here I'm just going to have the momentum acting on this, and then the amplitude. But this now will just measure the momentum of the gravitons. So this object is very simple to understand. So this object is just kind of kx mu, and then the cross-section for production of these gravitational waves, because this will just give me this factor of k, and then I will just have t and t dagger, just complex conjugate, okay, in the small q limit. So technically it would be like a cut. Where here I have the momentum kx crossing, but you can think of this essentially as this imaginary part of this amplitude, which is, by the optical theorem, the cross-section in the small q limit. Okay. So we find that the formula that we get for the radiated momentum is something that we could have written just in the quantum theory, right? So if we want to measure the momentum carried by the radiation, a natural formula to write would be as follows. So I just have the integral of kind of over the phase space of the outgoing gravitons. So let's say I have a single graviton for simplicity. And then just the momentum of that thing times the probability of emitting, right? So this is the probability of 2 to 2 plus gravitational waves. Okay, so this is something that we often measure in colliders. So in colliders, sometimes we don't measure directly a cross-section. We can measure the energy deposited in our detector over the whole measurement process. So this is this kind of observable. So here is the same. Okay, and this observable is purely radiative, unlike the other things that we had computed before. And notice that here we didn't have to think about the classical phase space, gauge conditions, anything like that, which is the advantage of doing the calculation in this language.
Julio, sorry, one
Yes.
question. I'm a little bit confused on the method, because now you have shown me that k-rad is that integral, but then shouldn't I, in order to build the integrand, write down the expression for each of the pieces, and how would I write this? The piece that I need to moduli square has an actual graviton going away. Shouldn't I, at the end of the day, build the phase space and build that okay?
Yeah, that's, I mean, when we computed the quantum theory, we just have particles outgoing in the final state, on-shell particles, right? So, and that we know how to compute. These are all gauge invariant. These amplitudes are gauge invariant.
Very good, very good.
Yeah,
Thanks.
so
thanks.
we don't need to worry
because,
about
because they are on shell, they are amplitudes.
Yes,
Yeah,
yes,
thank you very
exactly.
much. Thank you very much.
Yeah, there's another question.
Yeah, I have the similar question. At what point that redundancy of the gauge symmetry was hidden in the creation annihilation operator, or?
So kind of the redundance is that if you wanted to compute this using an action, what you should do is to compute the in expectation value of something like a pseudo-stress tensor for the radiation, which is a gauge-dependent quantity, right? And then take the limit when that goes to infinity, where it will become gauge invariant. Okay? So this formula here, it's the kind of the final output of that procedure, where we start with something which is gauge-dependent, and we take a limit where it becomes gauge invariant as a function of purely on-shell data. Right? And actually, we'll see this now for the waveform. So the last thing I'm going to do is just to argue the same for the waveform. And there, I'll explain just in a little bit more detail. Okay, this formula, I think it's clear. Sorry, again, I forgot the momentum, but which is important. Otherwise, it was just the number of gravitons emitted. But we'll see how an analogous formula arises for the waveform, right? So what is the waveform? So the waveform for the gravitational radiation, and let me choose the waveform with some fixed helicity. Okay, so this will be a function of what? It will be a function of the direction of the celestial sphere, and maybe of some frequency. So let me choose the spectral waveform. Actually, let me just first write it as a function of time. So this will be the limit when r goes to infinity of r times the gravitational field contracted with the appropriate polarizations, where this is at time t, and then I'm just choosing x to be r times some unit vector, okay? So I'm just taking the gravitational field at some point in space, and I'm just sending r to infinity to measure it at infinity. Okay? So if you want to be more careful, you can choose this to be retarded time or something like that, but let me just be schematic. Okay, what is this h mu nu connected with these polarizations? This is a simple object, because we can use, when r is very large, we can use the free field expansion of the gravitational field in terms of creation and annihilation operators. Let me just write x. So this will be simply ddk, so integral over on-shell particles, and then e to the I k dot x, annihilation operator with momentum k and helicity h, plus e to the minus I k dot x, a dagger h. Okay. So of course, this is not really gauge invariant, because if I didn't contract with these polarizations, there will be polarizations on the right-hand side here, which depend on the gauge. I could do a gauge transformation that shifts those polarizations, right? But then there's something nice that happens when I take this limit. This is dominated by when the region of the integration where this phase is stationary. Okay, so I could write k mu as kind of omega. So it's on shell, so I can write as omega times some direction. And then x, we said that it's just time Rn. Okay, and it turns out that if I take r to be large with fixed t, this is going to be dominated by the stationary phase of this integral. And the stationary phase is when nk dot n is 0. Okay, when the two directions are aligned. Okay, so I'll leave that as an exercise because I don't have much time, but this is the. So what one finds is that the right operator that computes this waveform is the following. So I have this limit when r goes to infinity, r, and then the stationary phase, there's also some contribution from the fluctuations around this point, as usual, so just some kind of quote-unquote one-loop determinant. that gives me 1 over 4 pi I r, integral from 0 to infinity. So you can fill in the details, but this is just the result of this stationary phase calculation. E to the I omega t, and now just the annihilation operator with momentum equals omega n. So the direction in the celestial sphere that I had chosen when I took the limit, and the fixed helicity. This was the fixed helicity. Okay, so here again, we started with something which is not gauge invariant, which is these linearized perturbations of gravitational field, and I explicitly took the limit and find that there's some simple operator, which is just the annihilation operator for 1 graviton. Okay, so now we can measure this. So now we want to plug this into this KMOC formula. Once again, there won't be anything in the initial state, right? But now we have to be careful because we have a annihilation operator. So this, when it acts on some state, it can just create a particle, right? So what's going to be our formula? There will be 2 contributions, as usual. So let me just write the integrand. So here I had the commutator here of f with t. Okay, so this has an annihilation operator. So the commutator, only the term when this is on the left will contribute, because when it acts on the right, the annihilation operator will annihilate the state, because we don't have any gravitons. So the only contribution will be this, for the first term of our formula for the observable. And this is something very simple, because this, the annihilation operator acting on the left-hand side is just going to create a graviton, right? So what is this object? This object will be this kind of 1 over 4 pi I let me just, let me call it a graviton that will have momentum, which goes like omega n, maybe more explicit, omega n, and helicity little h. P1, P2, this is just the 5-point amplitude. This is literally just P1, P2, K, P3. Sorry. There's a, no, sorry, there's a T, yeah. Otherwise, there's no amplitude, yeah. Okay, so we find that the first term just gives us literally the 5-point amplitude. And indeed, at leading order, this will be the answer. So the answer is that the leading order waveform is simply the Fourier transform of the 5-point scattering amplitude, which is a very nice result. There's a question. That canceled when I took the, that comes from the fluctuations around this point. So here I didn't do the stationary phase calculation carefully, but basically the idea is that in here you have an integral over angles. See here you just have an integral over omega. So you have an integral over these angles, and k, right? It's dominated by a saddle, which is when the angle between these two is 0, right? But of course you need to expand around that, and there's a Gaussian integral left over that gives this 1 over r. Yeah. Okay, and then just schematically, the second term, I won't do the calculation in detail, but you can imagine from our previous calculation for the impulse. So the second term, which only starts at kind kind of second order imperturbation theory, it will look something like this. It will be a contribution where again I have P1, P2, P3, P4, some graviton with fixed momentum K, because again I will have some annihilation operator that creates something in the intermediate state. But remember, the formula had a term with like T dagger X, and then X with O, which in this case is F with T. So you only have the 5-point amplitude on one side of the cut. Okay. So this looks like a cut of the 5-point amplitude, just like before, but this starts at high orders. And again, this will have a role of canceling some 1/h bars, and it includes the possibility that there's additional radiation in the final state. Okay, so we didn't discuss how to compute the 5-point amplitude in detail, but okay, if you compute it, literally that is the waveform. Any questions about this? I'm just going to conclude with some general comments about how to incorporate this also in this framework of this exponential form of the S matrix, which seemed that kind of could only handle the 4-point amplitude, but any questions about this formula? Yes.
Thank you. The states from the A operator, there are only on-shell states, because you said before create gravitons.
Yeah. So this is integrated over the on-shell phase space.
Yeah.
Yeah.
But radiation states is from these operators only?
I'm not sure I understand the question. So you have to distinguish the state and the measurement. Okay, so the state X is some state that includes everything, includes radiation, the original particles, right? But because we are using this in-informalism, we don't have to choose a final state. So that's the difference between measuring an observable and the amplitude. So the amplitude, we had to choose the final state, right? We had the 4-point amplitude. Now we have the 5-point amplitude, where we need to choose a different final state, right? But when we compute things with this sandwich of the S matrix, right, we just have to sum over all possible final states, which will include just the 2 particles or the 2 particles with radiation, right? So this X could be empty also. This additional radiation could be just not there. So you have to sum over all possibilities. So the state always includes radiation because I have to sum over all the final states. The important question is, what am I measuring, right? What is the observable that I'm trying to calculate, right? And for instance, in one of them, it was just the impulse, right? So kind of this, there were some contributions from radiation, but we were not measuring a property of the radiation directly. Here we are measuring this waveform, F, and we are literally measuring a property of the radiation. We are measuring the radiative field at infinity.
Okay. Okay, thank you.
Why do you say that the momentum that you had in the previous formula was not a property of, why is not that K? In the previous
that one was. So the first formula that I gave, which was the impulse of a particle, that was like a property of the particles that just scattered.
Yes.
Right? And of course, if they emit radiation, they won't conserve momentum, so you would see indirectly that there was radiation. Then I gave you a formula for the momentum radiated, which was really a property of the radiation. So there you were measuring.
So why didn't it have something like that?
Because it was quadratic in the creation annihilation operators, right? So you see, there's a different, like this kind of measurement where you have A dagger A, you're counting gravitons, right? And you're just counting them weighted by their energy. So that was kind of this formula with the cross section. So I'm just saying, how many do I have, and how much energy does each one of them carry? This one is not counting anything. This is literally measuring the radiation. That's why it looks like a 5-point amplitude, right? And it was linear in the creation annihilation operators.
So physically, you have the same process in mind, but the actual computation is based on different diagrams.
Yes, yes, because the observable is different. So in one case, any particle that was emitted in the final state, right, it had to appear on the other side because I was just measuring some probability of something weighted. This is slightly different measurement, yeah. And just as a side comment, so recently there were some nice papers by Simon Caron-Huot and Sebastian Misera and Hofi Hannes-Dotter where they actually realized that these things are related to scattering amplitudes by analytic continuation. So these are not disconnected from the space of amplitudes. So I told you a couple lectures ago that amplitudes were analytic functions of complex momenta, so you can explore what values they take out there in the complex plane. And it turns out that that these kind of measurements of kind of one particle creation annihilation operators, they're related kind of by analytic continuation to scattering amplitudes. Unfortunately, to do that analytic continuation, you need to go into the kind of quantum part of the kinematics. So you cannot just compute the classical limit of an amplitude and then analytically continue and get for free the classical observable. So even though it's a very nice observation, and I think it's a very deep fact, I think for practical calculations doesn't help very much. But yeah, this is at the end of the day is very closely related to a scattering amplitude. This one is literally the amplitude, but we have this extra contribution, and that has to do with this analytic continuation. Yeah. Okay. Any more questions? So I'll just make one last comment about exponentiation. So I told you that it was nice to write the amplitude in the classical limit as e to the I n over h bar. But it seemed that this was only helpful when we had like 4-point amplitudes, but in fact, it's not. In fact, one can show that if you look at these 5-point amplitudes and then you do the sort of classical analysis that we did before, then there will also be some exponentiation of the 5-point amplitude and also of higher point amplitudes in the classical limit. So for instance, the 5-point amplitude, what you will learn is that this n, a leading order will be this classical action times basically creation annihilation operators for the particles, so that it just gives me this as an expectation value. So this would be like particle 1, particle 2, A3, A4. Right? So this is just guarantees that the expectation value in a 4-particle state is just I. Right? But there's going to be a correction to this, which will be of the form, so let me just call this capital A for simplicity. So this will be, I still have these particles, but then there's something that looks like this. So this F is the classical waveform, okay? And these are creation annihilation operators for the gravitons. So because this appears in the exponential, right? So this is telling you that this goes like e to this I times A plus something that looks like kind of A dagger H plus A H star, roughly. And what is the name of this? Does anybody know what kind of state is created by this operator? So this is the S matrix. So if I act with this on an initial state, it will create some state with final radiation.
Coherent?
Yes. So this is a coherent state. Okay. So this exponentiation actually continues to hold for higher point amplitudes. And if now you plug this in to the K-Mosi formula, you will see that precisely it would extract this function, F. This function F, which is just now a number, this is not an operator, which is the classical waveform, okay? So as expected, some classical wave actually should arise as a coherent state of particles, just like in electromagnetism, okay? And one can show indeed that this is the case at the leading order. But actually, GR is a bit more interesting because GR is nonlinear. So since maybe a month ago, people have started to realize that this is not the end of the story. So even to describe classical radiation, because of nonlinearities in GR, there can be like various correlations between the waves, the signals at various detectors that just come from the fact that GR is nonlinear. So you could have a gravitational wave which is emitted by some source, and then it just splits into two because GR is nonlinear. So this is not the end of the story. So there's a ... which is pretty much completely unexplored. Okay. Okay. So I think with that I will end the lectures. Hopefully you understood a little bit about classical GR and its connection to quantum amplitudes. And if you have any questions, I'll be happy to answer them.
We thank Julio. I'm here to run, so you're...
Thank you very much for the lectures. I would like to make a question about this very last statement in which you talked about wave splitting. Is this somehow related to the nonlinear memory effect, and could you compute it using these methods?
It's precisely related to nonlinear memory, and that's how we realized that. So for those who don't know, first of all, the linear memory is the fact that this function here, which is a function of time, there's a quantity which is called the memory, which is very simple to understand. It's just the total change in the waveform. So kind of the memory so let me just fix the helicity. This is just like f at t equals plus infinity minus f at t equals minus infinity. Okay, and the picture is that if you have some time series for your waveform, like the ones at LIGO, so often we see that they look like this, and they go back to the baseline, but actually that's not what really happens. What happens is that they oscillate, and then they will go back to like a different position. So that means that if you had two mirrors, when a gravitational wave passes, the position of the mirrors will shift by a finite amount. Okay? And there's two contributions to this. There's a contribution. So this is related famously to soft theorems, right? And there's two contributions. There's a contributions which just come from the soft radiation emitted by each one of the particles in the process. Okay, so this is given by Weinberg's soft theorem. So there's some nice all-order formula that tells you that this linear memory is kind of the sum over all of the particles of p I dot epsilon over kind of n dot p I, where these are the initial and the final momenta. So it depends on these impulses. So this is a non-perturbative formula. If you know the initial and the final momenta, I told you how to compute the change, then you can compute this linear part to any order in perturbation theory. But there's an extra contribution, which is the soft radiation emitted by the hard gravitons. Okay, so there's another contribution, which is a nonlinear contribution. And this one roughly looks like this. So it roughly looks like the integral, again, over some graviton phase space. Or actually, let me be even more schematic. So this will be like an integral with some density over k. So what is this density? This density is essentially related to the power spectrum of the radiation, right? So this is kind of the number of gravitons with momentum k, so the expectation value of A dagger A, weighted by this soft factor. Okay, so now I have like k dot epsilon squared, k dot n, but this depends on the spectrum of the gravitational radiation. Right? So this looks, actually, this is inside that diagram I wrote there. So inside of this diagram, there's going to be a contribution that comes from an emission from one of the hard gravitons in the final state. Okay, so this was known kind of in the small velocity limit, and in a paper that we put out last week, we actually computed this in this post-Minkowskian regime, and it's definitely not zero. And as far as we can tell, it cannot be reproduced by this coherent state formula that I wrote. So this needs to be modified, and this is just for soft radiation. So it's just the first indication that nonlinearities will give rise to correlations. But we think that this might be more general, and that to understand all of these kind of multiple gravitons in the final state, one will need to modify these coherent ansatz. And by the way, this doesn't happen in electromagnetism. So in electromagnetism, radiation is always coherent because there's no nonlinearities. It's a linear theory, right? So the radiation cannot emit further radiation. Only charged particles can emit radiation. But remember, yesterday we were discussing that there were kind of two kinds of radiation in GR. There was just the radiation from accelerated particles that have energy, but there was also radiation from nonlinearities. So that's a reflection of the same fact.
Thank you.
I have two basic questions. One, before the KMOC formalism, for the people from amplitude community, did they compute the deflection angle?
People have computed the deflection angle. So the question is whether some of these observables were known before we came in. And they were known at the second, to many orders in the post-Newtonian limit. So in this low velocity expansion, these were known, basically roughly up to the 5th order in the post-Newtonian limit. But in the post-Minkowskian expansion, so weak field, but all orders in velocity, the only results that were available were at the 2nd order. So just g squared, right? And now we are at g to the 5 for most things. So these methods have really pushed the state of the art. And it's for various technical reasons. It's because, so at the end of the day, the hardest part of these computations is the part that I didn't discuss at all in these lectures, which is how to compute some of these integrals, starting at 2 loops, okay? But turns out that there's a huge amount of machinery from collider physics that teaches us how to compute things like this. And I would say that's been the kind of biggest crutch that we've had to really push the state of the art. Yeah.
And the other question, maybe it's about the same thing. It's very amazing the sort of concrete results that you find along this approach. But shouldn't, for the people who just think of the two-body problem in GR, suppose they don't know anything about quantum mechanics. It's a classical problem, classical mathematical problem. Shouldn't there be some kind of match of these quantum calculations into the realm of classical physics?
Yes, so kind of after the first push of these amplitude methods, there's been kind of an alternative way of setting up the calculation, which uses point particles, so word lines instead of like quantum particles like I described. And people have done also, in fact, some of the state-of-the-art calculations have been done using that, which kind of computes directly the logarithm of these observables. So it avoids these issues with these terms that exponentiate, and it directly computes the classical part. So there is a purely classical calculation that can be set up, but as a matter of fact, that was motivated by, in part, by thinking about it purely on shell directly. So amplitudes people tell you shouldn't compute things like the Hamiltonian or the potential or the forces between the particles, because as we were discussing earlier, they're gauge dependent. This is what typically was done in the classical GR literature, and then those were used to compute observables. One of the insights is if you focus directly on the observable, which is gauge invariant, that object is very nice and much more computable and unambiguous. And so now there's also kind of counterpart to these amplitudes computations using purely classical methods, but that also leverage some of this machinery from collider physics for integration and other things.
Thank you.
I have one extra, a follow-up of his question. You said that these nonlinearities gave rise to a correction in the ansatz of the coherent state. But yesterday I also asked you regarding this non-abelian gauge theory. So this fact was also not found by previous computation non-abelian gauge theories, right? Because the coherent answer would also be wrong in that case.
Yes,
if you are
yes.
interested. Okay.
And this is important for kind of situations in which kind of radiation of gluons classicalizes, which doesn't happen, for instance, in the LHC, but if you have like heavy ion colliders where there's some like semi-classical state that can control various features, then I expect that the same thing will.
Very good, very good. Thanks, thanks.
Since you mentioned memory effects, is there a way of writing those amplitudes as correlators in the celestial sphere or something like that?
Probably. Let me leave it at that.
Okay, so we thank Julio again. We meet him again here at 11:30.
Also, you don't need to count, you can just count powers of 3.